You guys have any questions or anything? What we've been doing?
Question one on the homework, where do you want us to start deriving equation one from?
Oh, all right. So let's see, it's a persistence length thing, so it's at the end of this. Here. So that's a good question. I mean, it's anyway, so there's two part, it says two though. So anyway, this is what you have to do is like say, well, it's a linear, so where does like that equation come from? Right? So that's just a linear, kind of a linear absorption model. So it's the same as if you had like when you talk about linear absorption for light, like Beer's law, they call this. And that's the absorption coefficient alpha, which has units of 1 over length. So 1 over alpha is like a persistence length for the light kind of. It's kind of 1 over alpha is kind of a persistence length for the light passing through something, I guess you could say. It's got the same units, it would be length. So basically, instead of, so swap out, so where that comes from is that the change in the light that goes through is proportional to how much light shined in at first. So if I shine brighter light, I get a bigger change. So, and it's also proportional to how thick the stuff is that it's passing through the material. So anyway, so that's a linear relationship between the change and the thing, which gives you this d thing over thing, which integral, that's the log. Right, so that's how you get an exponent. If you take an exponential both sides, you get I is I naught x, you get Beer's law. So that's why Beer's law is an exponential, but it's called a linear absorption law. This is kind of a linear resistance law someplace here. So I'll just do the same for that, like this is, so you have the change in this correlation between 2 points on the chain. So you have the chain, it's like a squiggly line. You take a point here and then a point some distance s along the contour of it. And you say dot the tangent there and the tangent there, dot product of the two. So if it's the same place, the dot product is a cosine of 0 degrees if it's the same. So that's cosine of 0 is 1. So if you're at 0, if s is 0, you have a value of 1. And if you average for all that, say s is 3, and average for all the pairs that are 3 apart, so average all those dot products, that number will be smaller than 1, because there'll be some of them that aren't perfectly parallel. Some will be offset and the cosine decays as you go off an angle. So basically, it has to be smaller. If you go to infinity s away, it's completely randomly oriented. That means the average would be like 0. So it's going to go from 1 to 0. This dot product has to go from 1 to 0, whatever the dot product is. Oops. That dot product would go from 1 to 0 when s is 0. It's 1. When s is infinity, it's 0. The average of all those dot products between the tangents. So it has to decay from 1 to 0. And if you say, well, if it's strongly correlated, then I'm going to get a bigger change in that. I change s because I change the distance between the points, just like I did the same thing that I did here. So the bigger the correlation, the stronger the change in the correlation, meaning it's a linear law. It's a linear relationship. That's the simplest assumption you can make about something that changes. It's called a linear law. So they talk about nonlinear optical components, means that it doesn't follow that law. There's like a square term or a cube term. It'll depend on the cube of the intensity or the square of the intensity. Those are nonlinear optics, I call that. This is linear optics. It's like there's advantages for nonlinear optics. They use them for like something. They use them to do something, sensors or something or other, right? So, but these are linear optics because it's, follows that linear law. This is also a linear law. So if you take that, it'll be d this over that. That gives you log of that thing equals s, and s would be integrated from 0 to s. equal like S over LP. So you have S over LP. It's a decay, so this thing decays, so it's a negative here. Just like this thing, the intensity also decays, so it's a negative. Right, so that's where the negative means it's a decaying function. Okay, so that's it. So you integrate that d that over that, gives you log of that, and then you take an exponential both sides, you get that thing. That's the first part. The second part is you need to say like you want to calculate, so the average of that thing would be oops. The average of that thing should give you 0. Like if you look at enough chains, that should give you 0. The integral of that tangent ds gives you the length, gives you like the length of the distance between the ends of the chain. The integral of that tangents, since the tangent is the derivative of the position with space, if you integrate it over the space, over the correlation, over the contour, then you'll get the end-to-end distance of the chain, like what the path led to between there to there, which on average would be 0. I mean, if you averaged a bunch of chains, you get 0 for that. And if you want to get, so that's a useless number. So you want to get R squared, which is the thing we got before, which was NL squared before, N Kun L Kun squared. So to get that, you plug in this integral into that, do a dot product of those two, mess around with the math. You know what that dot is, that's this exponential decay, plug that in, do the double integral of that, and you get this kind of like messy function. So you just have to parrot whatever I did here. I'm just asking you to go through this and kind of convince yourself that you have some kind of handle on it a little bit to get to this equation. Then once you get there, then you have to say, well, that's a mess, but the thing I have for the other one is pretty simple. It's NL squared. So how do the two relate? So you say, so there's no assumption about a Gaussian chain here. That's one thing. I never said anything about random walk. It could be a self-avoiding chain. It could be anything. Just says there's some kind of correlation function that follows a linear decay function. There's nothing. I never said Gaussian. I never said random. I didn't say anything like that. So this is kind of more useful in a sense. The other one relies on a pretty strict thing. It has to be a random walk. It has to have no excluded volume. So this is a more flexible model for the chain. Right? It's called the persistent chain model. Anyway, so how do the two relate? So if you have a chain that's of infinite length, so you get this messy equation, but it simplifies. So you have a nice simple thing out front, and then you have this messy thing. So L's the contour length. If you have an infinite chain, L's infinity. Like how long is it? When you stretch it fully out, it will be infinite if it's infinite. And LP is fixed value, so that thing has to go to 0. And also e to the minus infinity is 0, so you'd have 1 here. So basically 1 times 0 gives 0. That thing drops out. You just have this prefactor for an infinite chain. Right. So if you take this thing, says you have a Gaussian or random walk chain made up of steps that are fixed length, LK. This thing says if you assume that you get rid of this term, it means you have an infinite chain. So you have an infinite Gaussian chain in order to make this thing work. Because this part is Gaussian, this part is infinite, in order to simplify that equation. Then you can say NK times LK is capital L, then just have LK times capital L. And then this thing's 2LP, so 2LP has to equal LK for an infinite chain, infinite Gaussian chain. Gaussian come from here, infinite come from there. Right, so those are like the limits of it. All right, so they use that. So in this paper, they use that equation somewhere. They use it. Oops. So here, this is their dot product of the vectors, and this is their exponential. That's their linear decay law. Right, and NP, instead of saying LP, they use the number of steps in a persistent unit, which would be kind of the same thing as a C infinity. Now C infinity is the LP divided by LK. So it's kind of like the number of LKs in LP. So it's kind of like C infinity, this NP, more or less. So that like equation 1 is just that derivation. So just said like go through it. So they're looking at, is that okay? Or
like.
Oh, yeah.
It's more easy to get equation one.
Yeah, it's just asking you to go through slide 78, 79, 80. That's it. And then that stuff is also in this paper by Yitra, which is somewhere on the webpage, but I don't know where he goes through exactly that. And it's also, oh, it's also in the appendix of Flory 2 book, which I don't have up online. It's in Yamakawa's book online. That is online. And it's also in this called the Kraki-Perrode worm-like chain model. So these are Austrians from Graz, Austria, which is like in the middle of Austria, the iron capital of Austria. So somehow that became a capital for this kind of scattering things for some reason. Anyway, Perrode is like a genius and Kraki was a student. I think they both got old and died. So it's like in the 60s, whatever. So LP, they kind of came up with this model. Anyway, that's also in, anyway, if you want to read that, the derivation of that, it's in Strobel, it's in like a few of the books. I don't know, probably what you got is good enough, I think. So anyway, so I wanted to find something on conducting polymers and then, so this group, this Ying Dao is at Illinois, UIUC, so Urbana-Champaign. The whole group is from there except for Baiyang Du Li, who's a guy from Argonne that works at the synchrotron, which is where they have high intensity X-rays. So the measurements, some of the measurements were done there. And I think he probably had a hand in either this Kwok guy who I don't know or Baiyang Du wrote the scattering thing, because the scattering thing is really well written in this. Usually it isn't. Usually it's like a hack job. But basically, it's a really messy system, but basically they put it together kind of reasonably. So anyway, one of these two guys is pretty good. Hard to tell, or maybe the two of them together. But Kwok, I guess I looked up as like a kind of like a research scientist. Means like he's kind of like not a professor. And then Ying Dao is like a big time professor at Illinois. Anyway, so they're looking at this. So they also in the same year they published this paper in Nature, which is like the top journal, you know. So it helps if you're from Illinois, because it's like every engineering department in Illinois is in the top 10 in the country. So it's kind of like the best school, I guess. I think they beat MIT for that, but it's also in the middle of a cornfield. So I think you'd commit suicide if you were there. So it's kind of like go to the best place or commit suicide, you know, make your choice. So anyway, I think everyone that lives there like learns to fly a plane because it's like you got to get out of that place. So this polymer, so this is a thiophene with the sulfur. See, there's conjugations. You have single, double, single, double, single, double, and the single and doubles will have resonance structures. So this can go double, that can go single. So it'll flip back and forth. And the electrons have mobility if you kind of give them a kick. So it'll conduct if you put in something that dopes it, like a donor, electron donor. So usually you could add in another material to this that could donate electrons, and then it would switch it from insulator to conductor, right? But some polymers have built in, so there can be polymer pairs that one's a donor, one's an acceptor. There can be a low molecular weight that's a donor and a polymer that's an acceptor, or you can have a polymer that's a donor, acceptor, both. So this is a combo package, right? So, and then, so if you have this rigid backbone, it's completely insoluble. So polythiophenes, just like you make it electrochemically and that's it. You can't do anything with it after you're done making it. It's like polyacetylene, it's just permanently made. So you polymerize these, put an electric field, and you actually polymerize it under an electric field. Anyway, so that's these all are kind of categories of that. So in order to make it soluble, they stick things on. So that the classic one is this P3 HT, this thing. So you see polythiophene, and they put on 1, 2, 3, 4, so a hexane alkane onto the side. And then so people like you can add anything onto the side. So add a lot of different things. the trick is to put something on that doesn't mess up the conjugation along here. So you don't want to have like a electron, like an aromatic ring would mess this up, would pull the electrons off, right? So, right, so that's like the classic conducting like that's like the second generation. The first generation conducting polymers were insoluble. They just made them and that's it. And then afterwards they started to stick things on to make them more soluble. So this complicates the system. It was already complicated because it's crystalline and it's made, the way you make it is a permanent structure. So it's however you synthesized it is how it is. And you can't, there's no processing to it after that. Anyway, so yeah, so they let's see. So this is a molecule, this is the main molecule they're working with. So it's, I forget the name of it, but it's got a bunch of letters with a P in it, right? So you can see these are, C12 is dodecane, that's candle wax. And C10 is another kind of wax. And they get double C10s on two sides of it. So these things do something that they don't know what, but basically they get a peak in the scattering pattern from those. So you can think, if you, like, so they call it, all right, they call it the lamellar peak, which is kind of odd. So, and I guess that's from the literature. So if you take candle wax, I said before, you're going to get something like this. So they form, and the reason why it's waxy is because they'll line up. So you have sheets that's like deck of cards will slide against each other, right? And if it's a polyethylene, then you get this chain folding business going on, kind of the same thing. So these are 12 carbons and they have like 10 carbons. They have a chain with 10 carbons sticking off like that. Then they have, so this would give rise to a lamellar peak in scattering. Like you'd see intensity, Q, and it'd be going along, and then like there'll be a peak due to this stacking of these things. Like this Q, 2 pi over that Q would be this long period, also called L sometimes, but like the stacking period of those. And that would be called a lamellar peak. So those chains, and they have this wax kind of hanging off like that, I guess. And maybe that thing can do something, but you'd think this would form like sheets like that, and maybe a sheet here. So you kind of think maybe there's a long period associated. Sorry to use the same symbol, but anyway, they call it a lamellar peak for whatever reason. They never give a cartoon like that, but this is in my mind what they're thinking of. And no one ever seems to give a cartoon for why they call it a lamellar peak, right? So, and it's a weak peak. Anyway, so the reason this is in nature is that they make this by putting that into solution. And so they're going to make a thin film to make like a sensor with this. Like the conductivity will change if nitrogen oxide comes near it. And it's very specific to just nitrogen oxide. You could use it in an exhaust system in a car or something. Or you could make it conducting a flexible electronic or something to put on your skin to do something, and you could implant it, whatever, right? So some kind of device you're going to make with it. Generally, it's a thin film. So when they make thin film, they put a solution, they let it dry. They notice that when it dries, it shows circular dichroism. Okay, so which is something you see in handed molecules. So if a molecule is tactic, so it's got left or right handedness to it, then it'll when polarized light passes through it, it makes it circularly polarized. So there's like a video, there's a video under this homework from UCLA with this guy that shows kind of how circular polarization works. And he explains it like light will have like 2 electric field vectors. So you have one, and there's a magnetic field 90 degrees to this phase from it. So he's only showing the electric part. So linear polarized has 2 electric field vectors that are in phase with each other. And circularly polarized, one of those two, you can watch this whole thing. It's kind of marginally pretty kind of interesting. It's kind of a California version of this, but there used to be a really nice thing from Hungary. It was like a real, but the web link isn't there anymore. I tried to look for it. Basically, one of those 2 wave vectors is offset by half. So one of the 2 is offset by half a wavelength or a quarter wavelength. So it's called, you put it through what's called a quarter wave plate, which slows down one of the two vectors. Then it ends up that the light actually goes through like a circular helical, the electric field vector of the light goes through a circular rotation helix. And if you do that only partially, like it isn't a quarter wave, it's some other fraction, then it becomes elliptically. So it's not circular, it's elliptical. So if you shoot a beam, all right, so this is used in a machine called an ellipsometer, which can measure the thickness of a really thin film. There's a couple of them in the department. So you have a thin film, you shoot a beam of circularly polarized light into the film, and when it reflects like into the film, you kill off the light, and in the plane of the film, you don't. So it comes out, light reflecting off a surface becomes linearly polarized. Right. So if you go into a circular polarized, depending on the thickness of the film that's on it, it becomes elliptically polarized when it comes out. If you have another quarter wavelength plate to analyze it on the other end, you can figure out the degree to which it shifted the two things apart. Right. And you don't only normally see this in biomolecules and things that are handed molecules, like they're always made the same way. Anyway, so that's why they're starting with a non-chiral or non-handed molecule, and they end up with chiral structure coming out of the self-assembly of this thing, which is kind of interesting. The reason why it's in nature, like this would appeal to biologists, because normally they would only see this chirality in biomolecules. And then it appeals to like physicists because, oh, they're taking nothing and making something from it, like unhandedness, and then makes handedness just due to the self-assembly of the thing, which is odd. So there's a lot of appealing characteristics to this. Actual implementation or use is zero, right? So basically it's kind of an interesting thing. So this is how you get a paper in Nature. It's like a little twist on stuff, and it's kind of neat, like, oh, that's nifty, but it's a high enough level no one understands it except someone that's really knows the field or somewhat knows the field. So perfect for Nature. So they almost package this up for that, right? So bingo, they got that. So it's not exactly really a science, because reproducibility of this is difficult to see. Oh, I also put up, so there's a circular dichroism measurement. This depends on the wavelength of the light that goes in. So you get a pattern. This is a CD pattern for the things. There's also, like, you do CD microscopy and see the different structures, different regions that have the handleness. All right, so that's kind of an aside, but it's there. It's the same molecule, it's the same group, right? It's a different first author. So whoever Park grabbed the reins on this. If you get a paper in Nature, then everyone in the world wants you to get a lot of invited talks, and it's like kind of a big thing. So it's a good thing. Science, nature more than science, but both, So anyway, this Park got the wreath for that or whatever. Then this Kwok didn't, is more like a lower level research scientist, like not a professor, but not teaching, so just does research. So works on soft money, type thing. So anyway, so this is more like studying actually like what's going on in these systems, and they're so all the applications are going to be in solid state. You're going to make a film and use it as a sensor or a conducting electronic component or whatever, right? So, so they want to know the structure of these things, so they put them in solution. They don't go into solution very easily. You have to heat it to 150 C and then put it in dichlorobenzene. Or you can also put it into Decalin, I think they use. So they have two solvents. It really likes to go into dichlorobenzene at 150. The Decalin, the advantage of the Decalin is that this side, so this, all right, so when you dichlorobenzene, you get this lamellar, quote unquote, lamellar peak, which isn't well described, but it's a peak. And then when you, so this is intensity versus Q log log. Then when you go to Decalin, that peak like disappears, which they say is because the Decalin has an affinity for the waxy side groups, because it's kind of an alkane, it might be decane. So it's got an affinity for the side group, so it dissolves it. So it breaks apart the stacking or something. This is all like loosey-goosey. None of this is evidence-based except for the peak disappears and their minds, whatever they're thinking. So in fact, the whole thing's a little wishy-washy, but basically it's not, it's as good as you can do with a kind of featureless scattering curve. You know, so they drain quite a bit of information out of this. They miss a few points, but basically that's all right. So the first thing they do is they want to know the persistence length. I mean, I think it was more or less like afterwards they figured out they needed the persistence length. So what they do is they do that density functional theory, which is density of electrons around an atom, and they can calculate the interactions between these planar units on this molecule. So they're saying that this is conjugated through here, and somehow it can rotate about this bond. I guess the conjugation is broken there or something. So somehow they get two rotation angles on the, or three dihedral angles, which means like deck of cards in proteins, you have two cards connected at the corners, and they can rotate about that. Right? And they kind of have fixed, more or less fixed angles, depending on if they're in a beta sheet or if they're in alpha helix. So two main structures in proteins. So you can tell from this dihedral angle plot, you can tell the how much of the material is in beta sheets, how much in alpha helix, and some other couple other structures, but those are the two main ones, right? So usually you get this dihedral angle from the circular dichroism instrument, which has this quarter wave plate measurement at different wavelengths. That'll spit out the dihedral angles for a protein, and then you can make a dihedral angle plot and figure out the percent alpha helix beta sheet in the protein. So they're taking all that biology stuff and applying it to these molecules and saying we have dihedral angles too. And they measure them not with a circular dichroism, they measure them by doing a computer simulation of the electron clouds of these things and figure out what the dihedral angles are. This is just a probability, I think. Oh, no, this is the potential energy for rotating that thing around. So they have a potential energy for rotating it around. They can feed that into a LAMMPS program and say, like, make a walk with balls that have this rotational potential, and then just see where the walk goes. So they do that for 20 units. This picture is for more than that, but basically the ones that they get these plots from are for 20 units. So they go up to 20 here.
How the peak appear in the dihedral and dihedral potential? Because there is a peak around 90 degrees, right?
Mm-hmm.
And then it falls down. I mean, how it goes up and then how it goes up down.
This is the energy to spin this thing around. So it wants to be at the lowest energy. So it wants to be in the pit of this. And this is the penalty to rotate at 90 degrees. So I have the two cards. Somehow when they're 90 degrees apart, that's a high energy state. And then when they're whatever parallel, it's a low energy state. So low energy is a good one. The high energy is a bad one. And it's gonna just do a step and say, all right, I'm gonna let these things shake around molecular dynamics, and then I'm just gonna say, find the lowest energy or use the energy potentials to say drive the rotations, and then make a chain and make that happen, then LAMMPS will just do that for you. These things are all pre-programmed. Like this would be programmed mostly for biologists looking at dihedral angle potentials, but basically you can just co-opt it right into this. It's plug and play, more or less. Right. So these aren't like that sophisticated to do. Then they have low energies because you want to minimize the energy of the system. So each one of these Murray units has 3 dihedrals. You want to get the lowest energy you can get, right? But there's also KT involved. So it's being kicked by KT. If KT is up here, none of this matters. KT's right here, then it kind of matters. If KT's down here, it matters a lot. So it depends what the temperature of the system is, how this whole thing's going to play out. So you're bouncing off like a KT kick against these things are bouncing it back. Like this is how the spring is, it's spinning it around. Right. So anyway, so you do that and you can get these chains like this. This one's longer than their 20 because the 21 would look bad, right? 1, 2, 3, 4, 5, 10, 20. The 21 would only be like that long, like a little teeny chain. Right. So we know like that doesn't work because let's see, 53 or something. we know it doesn't work because we have this plot. We know like if you go to 20, you're not in the game, especially, so this is rigid. The bottom one is the rigid, so that's the top one here. So the one you never reach a plateau on is the rigid one, the one they're dealing with, and they only go to 20. So like, no way, you don't get a persistence length from that. You get like this end thing. You don't even know how much of the end thing you have. Like if you plot this length versus MD, you go up to 20. For none of the chains do you reach the plateau value, not even the linear one that doesn't have side chains. That's part A of the problem with this. Let's see, there's another plot like, anyway, there's some other plots like that, but so part B of the problem with this is when they simulate this, they don't, because it would take too much computational power to put wax chains onto the end of this, which are bigger than the main chain. They just put a methyl group there because that's simpler and faster, but it's not the same molecule at all, right? In other words, we know from this, so this would be like what you call a brush polymer, right? It's got side groups. We know that already, we know that wherever 53, we know that like if you're looking at brush polymers, so low density, high density, this would be a high density brush polymer. They're saying a linear polymer has the same persistence as a high density brush polymer, which that isn't true. And you can't use 20. You'd have to use something like 10,000. I mean, right. So the whole thing is like messed up. It isn't, so no one in review, like nobody kind of said anything about that because it's kind of nice they use density functional theory. They cite a guy named what's the guy's name? Milner, Scott Milner, who's like kind of a genius at NIST that does this kind of stuff. He does a lot of computer simulation things. And he's probably the only person that would be capable of using density functional and coupling it with dihedral and then figuring out about the persistence length. So they just copied his paper and did it here. So Milner is kind of like he's a really kind of a nice person, you know, and meek kind of, but basically citing him is he's got a lot of scientific clout. So they cite him in doing this, like you can't really argue with it. But basically this is totally pretty much bogus. Like this LP 7.5 is it's much higher, right? It's much higher than that probably. So anyway, so that happened. They did that. So they have that 7.5. And then they know how many Mur units they have in their actual polymers. They can calculate from that using they can calculate the radius of gyration using kind of the equation that we had for the persistent chain. I mean, it might be a little bit different. It's kind of the same thing. It's got the same limits. I think L's infinity. This term drops out. Somehow it ends up the same. I don't know. But so anyway, so anyway, they calculate the RG from that, and then from the RG, so from the RG they get, so from one thing, 2 pi over the RG, they get a Q. They say that's where the chain should be. That's 0.02, which would be right here. So they say they're chained if it was a random walk, or if it was a persistent chain, it would have an RG. It would have, so RG in this plot would be like a knee. So it'd be basically like boom, like a Gaussian peak and linear, but it would be just a knee here. So looking for a knee at 0.2 because of that calculation. Again, the calculation isn't right, but that's what they're looking for. So anyway, yeah, there's something there. Like there's kind of a knee sometimes in some of the data that they have on that. And then what they also calculate is the overlap concentration. So they take the mass of their big polymer, they take this RG, they cube it to get the volume, they take the mass of the volume, they get an overlap concentration of 10. A 10 to 20 meg per ml, they say. So they run their samples based on that, 20 to 1 meg per ml. So the game here is that if you have, so once you reach overlap concentration, we should see screening at the low end, so the curves should change, right? So if you take that plot and then digitize it, and then divide them by the concentration, so they get a pretty good story with that. So they have the thin ones are the original curves. So as you increase the concentration, it goes up. So you divide by concentration. So 10 by 10 takes it from this purple to that bold purple, right? So it's almost right on the 1%. And then 2 by 2 goes from that brown curve, and then it falls right on top of the 1%. The brown is right, you can't see it because it's right on top of the blue, which is the 1%. So basically that's a test to see if you've reached the overlap concentration. The 2 is fine. It's perfectly exactly the same, except there's a little bit of deviation in the lamellar stacking thing that they talk about. The weird thing is that they go to 20, which they say is within their overlap concentration they calculated, divide by 20 by 20, and you end up with this thing. So it's not falling on the other curve, like it isn't, there's some big difference. If you try to make it fall on the same curve, you get exactly the same as the 1% one, except out here, except the lamellar stacking thing, right? And then, so the others deviate a little bit here because when you go up in concentration, something at large sizes, coagulation happens or something happens. But the highest concentration one, no, it's exactly the same. If you figure out what concentration you're actually measuring with the X-rays, 250 mg per ml, not 20. So how could that happen? Like what's going on? Like how, if you go up to 20 mg per ml, you measure it, and the scattering has an inherent kind of way to test what your concentration is if the structure hasn't changed. The structure hasn't changed, but it's saying that you're at almost 12 times the concentration that you put in, meaning that somehow in the beam, the thing messed up, something messed up, like it precipitated out or something happened, or there's something going on that you don't know what it is. Like somehow it's appearing that your concentration you're measuring is actually 12 times higher than concentration you put in for whatever reason. So one of the questions is why. There isn't a clear answer why. It could be experimental error. That could be a potential answer. So anyway, let me get back over here. By digitizing plots is useful. I wanted to digitize this one, but I didn't have time. So this one is where he's saying he's going to erase the lamellar, quote unquote, lamellar peak by putting in decane. I guess I don't know if it's decane or decalin, but basically I think it's, anyway, something that's more soluble for the side groups. And yeah, the peak goes away. And he's got a knee, so that's like a Gugnier's law. So that would be flat and a knee and decay down. So that's the kind of shape you're looking for, is flat and then decay down, which forms a knee. So yeah, there's probably a Gugnier raised gyration there. And then there's probably one here too, right? So you can kind of start picking apart these things. So if you look at those curves, like the superimposed curves, so you have a power 1 here. And there's only one answer for power 1. It's a rod. So there's a large scale rod. And then that ends, and then you get minus 2.7. So you're looking for 2, or you're looking for 1.56. You get 2.7. Then way out here, there's like a little kind of minus 1 that's kind of buried in with this lamellar peak thing. So whether that's real or not, but you could say that's a persistence. So you could say maybe like right here could be the persistence length, somewhere in that region, like 2 pi over 0.12. I don't know what that is, but let me find out. I didn't do that. And then 0.12. So that's 52 angstrom, 5 nanometer. And he said he was at 7.2 nanometer from his 7.2 nanometer for the calculation. So it's about right. I mean, his calculation comes out kind of close to what you would say if you took the intercept of that thing and that minus 1, and you got that would be like 5, and he got 7.2. So whatever. It could be true, or this could just be an artifact related to this lamellar peak thing. Anyway, so that's the kind of idea. He has persistent chains, and then he has he or she. I mean, there's she's in this and he, so they, I guess. And then there's someone out here. So they say like, oh, there's 2 structures. There's a large scale network structure that you can see in you can see in AFM and SEM, so they have a kind of an elaborate method. So they take the polymer solution, they freeze it in propane and ethane, then they freeze dry it. So they raise the temperature and pull a vacuum and get the solvent gone. So they make an aerogel from it. Let's call an aerogel at that point. Then they do AFM and TEM on the aerogels that they got. They say these are the struts that are showing up like these. They measure the diameter of those struts, which are kind of linear, I guess. It comes out 1 in the thing, and this isn't 1. So this is kind of convoluted. So it wouldn't be exactly 1, but basically they say it's 1. And they get the diameter of this, and the diameter of that kind of matches whatever they get from that Grenier region at the low end of the curves, like this thing out at this end. So they say that's the diameter, and then it forms a rod. This is actually power 1, so it doesn't look like the micrograph. And they say then that's somehow out here. There's another one that's another persistence that's the actual chains, right? So they end up with this model. So they pick it apart like that, and then they finally get to this model someplace in here. There's a picture. So they have two structures, this large scale rod structure and the local chain structure like this. To say this is a power 1 at large scale, that's a power 1 at small scale, and that should be like coils. And then somehow those things associate with each other at the end. So in this kind of system, like where does the conductivity come from? I mean, there's two things here. Anyway, I guess the idea is that the struts are the thing that are conducting. That's kind of the idea. And that when you dry it out, those things form into better wires or something, Anyway, there's also nuances to even that kind of complicated scheme, right? So they have, if you look at different molecular weights, so they make these things at different molecular weights, and then they get this, like when they're at a low molecular weight, they get what we just saw, like they have -1 here, -1 there, some kind of thing in between this lamellar structure peak. Then when they go to high molecular weight, it doesn't look anything like it. So it's like A and B doesn't look like the same stuff, except they nitpick it and they say like, oh yeah, well, there's a little hump here. It's a little lamellar peak still there. And this thing is kind of that, whatever that persistence length thing was. And then because we've gone to higher molecular weight, it forms larger struts. And there's this kind of AFM, SEM evidence for it. Like they're saying this thing's different than that thing. So I don't know, you could, yeah.
Those SEM works like the SAS, that's the small angle X-ray. Do they work like the same way?
SEM's an electron microscope looking at the
Yeah.
surface, right? So you have the sample. No, this is a polymer in solution. You put it into dichlorobenzene or into Decolan. It's just floating around in solution, right? Then you take that solution, put it into liquid ethane, which is at like 0 K or something, super cold. And that completely locks it off and cools it so fast that the solvent doesn't crystallize. That's the key thing. So when they can cool it so fast, if the solvent crystallizes, it disrupts the structure. If the solid's amorphous, because you cooled it so fast, it doesn't disrupt the structure. And you pull a vacuum and slowly heat it up and get rid of the solvent. And you make it's called an aerogel at that point. So it's whatever the structure was in solution, just locked in, more or less, right? And then you do micrographs of that and you say that's what's in solution. I mean, whether you believe that or not, that's up to you, but basically they are saying it's the same thing. Right? I mean, it's probably as good as you could do, I guess, but yeah.
The significance of that's like caused by wax.
The wax is just, there's no wax added. There's just the chain itself has built-in wax groups to make it solubilize in dichlorobenzene. Right, incidentally, so they're using a gel permeation chromatography method. So you have columns with a gel in it and you push it super high pressure, the polymer through it. The polymer kind of diffuses through and the big ones come through faster because they can't diffuse into all the network things in the gel, and the small ones come through slower because they explore the whole thing. So you can get a molecular weight separation in that. But they do it at 150 C with dichlorobenzene. So that's a really expensive piece of equipment. That's $1 million for that thing. So normally only like polyolefin, because polyethylene, that's what the common solvent and temperatures are for something like polyethylene, polypropylene. It's like Lyondell has a high temperature GPC, but most universities like don't have that because it's going to be like $1 million for this machine. And the only thing of use is like polyethylene, which isn't a research material much, you know. So basically, somehow at Illinois, they got $1 million to buy this machine just to measure the molecular weight of this thing. No one else can do that really, you know. So anyways, it's kind of interesting, but they do get the molecular weight of it. So yeah,
How come we come into the branches?
well, like this GPC machine, you can get the molecular weight. So you can have different detectors on the end. One, so it's coming out in time, it's separating the molecular weight, and it's a dilute solution. So it's coming out in a little tube, and you can shoot a beam of light in, do light scattering, and get the rays of gyration and also the weight average molecular weight from light scattering. Then you can do an index refraction detector and calibrate it with some other polymer that you put through. So just how much stuff is there or not, yes or no. So it gives you a signal of that. And then you can do a rheology, so you can measure the viscosity, which is proportional to molecular weight to the, I guess, power 1 if it's dilute, right? So you have like 3 measures of molecular weight. One's a hydrodynamic size, one's a scattering size, like rays of gyration. You get the mass size. From those 3, if you know those 3 sizes, they're different for a branched polymer and a linear polymer. So you can figure out if it's branched or not that way. That's what commercially they do. I mean, in industry. Yeah.
In one of the plots, they use solvents of varying concentration. So I'm curious if the choice of solvents could affect some information of polymers or the solution entered by the X-ray.
Yeah, I mean, that's the point. That's what they're doing here. Like they go through, so they're going through this, one of them dissolves the side chain, quote, supposedly. I mean, there's not evidence for that, basically, because the peak disappears, and then the other one doesn't. So like that's different solvents, and they do different cuts, 80, 20, 40, 60, 10, 90. They go through the different cuts and they can see this gradually disappears, the peak, and something happens out here. In fact, this thing just disappears and then it seems to just go to, that's why I want to digitize this. I think that goes to a slope of 1 all the way through, which would tell you it's got like infinite persistence. Like we just saw the red curve, you'd say you have a chain of infinite persistence, and then something happens at the high end, like it phase up. So in other words, the red curve alone would tell you clusters of chains bundled up to make an infinite fiber, which kind of makes sense for rigid polymers. You know, so without the blue, you'd have just fibers. That's it. And they aren't single polymer chains, they're clustered up. I mean, because this is too steep out here. That's like a surface. You've seen a surface of it, not a molecule. Anyway, so there's a lot. Anyway, it's a good example of like so messy, you know, and they're picking it apart. Like the 2 papers, actually, the Nature and this are really good to contrast, because one is like, boom, flash, here's this thing, everyone's gonna love it. And that's so simple. It's like we can just self-assemble this. It'll make like a biological thing out of something that's just dirt, you know. And it's like it's almost like creating life, you know, something like that, you know, not exactly, pretty close to like creating life. You can make out of dirt, you know, something that's achiral, something that's chiral. You've kind of like, it's like the hand of God has touched my material, you know. So that's like nature. And then this is like, this stuff is an absolute nightmare. It's a complete mess. It's a garbage can of all this stuff. And we're going to go in with the most powerful analytic techniques in the world and pick apart at each little piece of it and come up with a story. Like there's 2 different approaches. One's like a salesman selling you a new car. The other one's trying to like hide the junk car all broken apart and like the muffler's falling off. So yeah, or wait, yeah.
Can you explain the laminar stacking pump again? I just didn't get that part.
They don't say, they just use the word lamellar stacking. Yeah, yeah. So they just use that phrase. they never explain it. And because the side chains are alkanes near wax size, you think of it as like sheet-like stacking of alkanes. No one ever explains it. Like they just say, in fact, they put it in quotes, a lamellar peak. So they don't explain it, you know. So it's just like you have to use your imagination. It could be a lot of other things. I mean, so what
Yeah, I was gonna say this.
Oh.
What does it mean for something's phenomenal?
sheet, like a sheet of paper. It's like if you have a stack of paper, there's a regular spacing of them. So if you shot an X-ray through that or light, if you could shoot light through it, it scatters too much to do that, but you'd see a peak would come out due to the stacking period of it. Because they're regularly arranged in 1D. So polyethylene's got crystals like that, you get a peak in the scattering. It's called a lamellar peak. Right. So that peak would be 100 angstrom. This peak is at 5 angstrom. So it's more like a molecular stacking peak, like you'd see in liquid crystals, which this is a liquid crystal. So it's kind of like, I don't know why they don't call it a liquid crystal peak, like an emetic peak or something like that. That would make more sense, actually. No, but anyway, let's see. Let me just go through. So there's a lot to this. I mean, basically fish through it and then fish through it and see what you can get. And then there's the questions here. Let me see what I got. I went through 1 already, right? Derive equation 1. B. So this is the problem about that you can't. So if you're only going to 20, you can't see, for a rigid chain, you can't see the persistence. So his calculation is kind of worthless. Like his calculation of persistence length in the context of all the simulations that were done is kind of meaningless, right? Because he doesn't have a long enough chain to get it. And he doesn't have a function that would predict from that short thing. And then this thing, what's a question? So why doesn't the 21 match up? There isn't an answer to that. You have to figure it out. I mean, maybe there's no answer. Maybe it's just that it's an experimental error. Everything else matches almost perfectly, meaning that you're below the overlap concentration to 2%. And then at 3%, you're seeing correlations, large scale correlations. So that, I mean, at 10% and 20%, there's definitely changes, meaning that there's correlations. In other words, if it was just a mean field screened out, then it would drop below. If it goes up, so if it matches, you're below the overlap concentration. If it doesn't match, you either have specific interactions and it's above, or you have mean field and it goes below. So you have, if this specific stacking of the things, and it'll go up. So the 10 and 20, the 10 and the 10 and 20 are going up. Now the 10 and 10 is going up. 10 and 2 are going up, I guess. So even 2 is above the overlap concentration. And then the 20 goes nuts. Like the 20 is insane. Like it's not a homogeneous system if you get 12 times the concentration you put in to get it to match. And then it matches up like it's just the dilute one. So you're only seeing the dilute. Anyway, so there's maybe those gigantic blobs that are off, you aren't hitting with the beam. And then you're hitting just what's left over, the low molecular weight ones. And then you can come up maybe with a story about what's going on with the 21. Like this is where you get to like, so
Why did you pick the 10 over the?
because he calculated 10 to 20 would be overlap. So 10's the low end of overlap.
Okay.
So strictly from his molecular dynamics, whatever he did. So it's just, he just said that. And then the way to do it would be to do this, what I did. And you can see like that all of them are beyond overlap and that there's something really weird going on with the 20. Like if they had just done this, so A, they didn't do this and they messed up. B, they did this and realized it was screwed up, so they didn't show it. Right? There's kind of 2 answers to this. B is the more likely one, because all the rest of it, they're pretty much going along line like the way this should go. And they get to this and they never do this, like divide by the concentration, like that's like the first thing you would do. And the referees never asked them to do that. You know, so that's a 2 strikes, you know, that. The 1.7 is this actual slope, like here, you're all the way through this, you're kind of looking for either rods or Gaussian. So the 2.7 is close to Gaussian. So I guess it's higher, so it's denser. So you don't see a random walk. So that could be the network of fiber, whatever. Or who knows what the 2.7 is. And then the one you're looking for, that's rods. So he sees like two persistent things. One's a large scale, which is this big thick thing, and the other one's a small scale down here, which is the chains themselves. So there's kind of evidence for those two there. The 2.7 is kind of weird, So you expect if it was just a chain, it would go like 1 and then 2. 2.7s for rigid chains, that's kind of weird. Like that isn't really expected. And then the one here, that could be their network, and it goes to 1.7 when you get a higher concentration, meaning that the ones that are higher concentration are more convoluted network. They have a more crumpled rods, I guess. But basically, this should, if it's below overlap, these should fall exactly on top of each other, like the 20 divided by 250 matches with the 1%, and the others are all above overlap. So that means that whatever they said about being a dilute isn't true. But anyway, let me see what else we got here. Figure 2B. Let me just look for a second here. Figure 2B. So 2B, he's trying to get the persistence length from this thing, and that basically you can't exactly get it because he doesn't have the dimensions aren't right of the thing. So he's not really looking at a chain. He gets it from it, and he says it agrees with the simulation. So this is also like signatures of how you do papers. Like you got the simulation, you're sure it's 7 angstrom, 7 nanometer persistence. Then you have the data, and it's kind of iffy, but yeah, you can see it. Then you say like, I see it. That's what he does in figure 2B. So, and then he says it's based on Gurnier's model. So you look at that plot and you say, you're looking for knees. So he's in this region, like there's no knee, right? In other words, there's a knee for the red, but there's no knee for the blue. There's a knee for the blue, but there's no knee for the red. He's saying there's a knee in all of these, and that's how he can get the rate of gyration. And then he uses rate of gyration to get the diameter of the tube, but the rate of gyration isn't the diameter of the tube. It's the diameter of the tube divided by the square root of 12. It's like, that's not how you get the diameter of the tube. It's not the radius of gyration. That's not it. There's a scattering function for tubes, and it isn't the radius of gyration. It's the tube. Anyway, the last one, that's what the last one is. It should be, random walk, blah, blah, blah. So yeah, he's loosey-goosey with like the sizes. Like the size isn't the radius of the size of the coil isn't the radius of gyration. It's the size of the coils, the square root of 6 times the radius of gyration. Then the size of the tube isn't the radius of gyration, it's the radius of gyration divided by square root of 12. It's like the numbers are all messed up. Like he's just using radius of gyration through it. If you look through the supplemental and everything, it's just straight the Gurnier radius that he uses, which isn't the number he's saying it is. If you can't draw a cartoon with a Gurnier radius as the diameter of the tube, that's not the right number. Right, so he's pretty loosey-goosey overall with that, but anyway, that's it. Thanks.
Yeah.